Hello, Stat 300, and this is Professor Gonzalez, and I'd like to do some problems from 4.1 and 4.2. And these two problems, or these two sections, are coming from the adaptive side of ALEKS. So there's, I think, 6 questions in this chapter 4, summarizing bivariate data, and this is on the adaptive side of ALEKS. Once again, you can get to that by going to the menu on the left and clicking on Learn. And here's some of those questions. Now, I would like to do a little bit of background information, kind of little mini lecture for this. We're talking about correlation and causation and least squares regression lines, stuff like that. So let's take a look. So we have some associations, and this is called a correlation. It says two variables are how big is this thing going to be? That'll work. Two variables are positively associated if large values of one variable are associated with large values of the other variable. And so you can see if we were going to make some sort of line of best fit, something like that, that's not perfect, but then you can show that as this x value gets large, this y value also gets large, and so this is a positive correlation. Another way to see that positive correlation is when you look from left to right, the line is going up. And then we also have two variables are negatively associated, or they have a negative correlation, if the large variable of one variable are associated with small variables of the other variable. So as x gets large this way, y gets smaller this way, and this causes us to have this, if we did a line of best fit, we're just of course eyeballing it at this point. You can see that this is, as you read from left to right, it's going down, and this is considered a negative association or negative correlation. Two variables have a linear relationship if the data tends to cluster around a straight line when you plot the scatter plot. Okay, so when you plot the scatter plot, you can definitely see sort of some clustering around a straight line. So that's how we can see that it has a positive or negative correlation. In fact, our language could be something like this. I saw this and decided to put this in. It says, when you have a perfect positive correlation, that's when you have a perfect straight line. That's a perfect positive correlation. It's positive because it's going up when you're reading from left to right. That's this guy. And then the second slide here, it says a strong positive correlation. Now it's still positive because it's going up as we're going left to right, but it's not all in a straight perfect line, right? There's some variation there. So it's still a very strong positive correlation. Now, number 3, I'd call that a weak correlation. Still, you can see some sort of trend or correlation or association still in the positive direction as x gets larger, y gets larger, but it's a weaker positive correlation. And then on number 4, there's just like a shotgun, just dots all over the place, so there's no correlation. Number 5 be an example of a weak negative correlation. Once again, you can kind of start to see that we have, as x gets larger, y gets smaller, so that's a weak negative correlation. And on number 6, we'd say that that's a strong negative correlation because it's getting closer and closer to a perfect line. And number 7, we'd say that's a perfect negative correlation because all the dots plotted make a perfect straight line in the negative downward slope, so it's a negative. All right, so remember we're talking about these correlation, okay. Number 1, first thing we want to do is just basically take the table below, shows the number of hours worked and the amount of money spent on entertainment by each of 7 students. Create a scatter plot of the data. Well, that's just plotting the points. No big deal. So hours worked is going to be for instance, like our x-axis, and amount spent on entertainment, sort of considered like our y-axis, or it is our y-axis in this case. So let's see, 1,3, no problem. 1,3, 1,3 is right there. Next one is 3, 2, 3, 2. So far, I really can't see much of a correlation. 6, 4. 6, 4. Looks like it's about right there. And then we move to 8, 5. 8, 5. Starting to look like a positive correlation, possibly. 8, 5. So we did that and 8, 5. Now we got 9, 9. And then we have 10, 8. And finally, we have 13, 10. Okay, so that's all they wanted us to do. If we take this a step further, you could probably start to see that I think I'm starting to see some sort of correlation here. You know, my last video that was from the HW, or was from the assignment side, HW homework 4.2, where we were finding the least squares regression line, y hat. They were giving us a bunch of information, and we used the formulas to come up with y hat. So y hat is that line of best fit, you know, that kind of comes through here, that tries to approximate that the best we can. You know, now we just eyeball it. That's not exactly y hat, but that's what y hat is. Y hat is going to be that line of best fit, and we can mathematically figure it out. And sometimes they want us just to eyeball it and see if we can sort of get an estimate. So, oh yeah, back there. So we would say that this has a positive correlation. Correlation coefficient. So correlation coefficient, a numerical measure of the strength of a linear relationship between two variables is called a correlation coefficient. Now the correlation coefficient variable that we use is R. I don't know why that doesn't show up right here. Correlation coefficient, we like to use R for that. R is the correlation coefficient. Okay, so R is the correlation coefficient. So these values here are really talking about R values. So when we have an R value that is negative 1, that is showing in fact, it's negative 1, so it's a perfect negative correlation. So we already saw what that looks like in a graph. That would just be a negative correlation, which looks something like that. And everything, you know, let's see. That would be an example where all the points are in a perfect line. And it's negative. That would be negative 1. So when an R value equals negative 1, that's kind of what you get. When an R value equals negative 0.5, it's getting closer to 0 and away from 1, right? Because remember what 0 looks like. 0 is just no correlation, so it's sort of all over the place. But R equals negative 5 is a negative correlation that's getting weaker, right? It's not as strong. So it's just going to have sort of this, you can still tell it's a negative correlation, but it's not all in a nice tight line. And then on the other side, when we say R equals positive 0.5, now it's a positive, you know, kind of weakish correlation, I guess. It's somewhere in there. This is really weak here. This is really strong. So it's somewhere in the middle. And so, you know, it might look something like this, where we can see that it's going up. So it definitely has a positive correlation, but it's not perfect. And then when we get to R equaling 1, positive 1, this is a perfect positive correlation. So that means that the points are going to make a perfect line. So hopefully that helps to understand the R values. When they talk about R value, which is the correlation coefficient, it's the R value. R is the variable that we use for that. I should put that up there, okay? So here's some properties of that R value, the correlation coefficient is always between -1 and 1. Okay, yeah, and you can see that there, right? The correlation coefficient does not depend on the units of the variables. Yeah, correlation coefficient, it doesn't matter if we're talking about gas mileage, or we're talking about someone's ability to make a basketball go in the hoop, or whatever the situation is. Doesn't matter about the units or the situation. It does not matter which variable is x and which variable is y. The correlation coefficient only measures the strength of the linear relationship. So, do these little dots, like ducks, fall in a row and have a very, very strong negative correlation, like -1? Or do they all fall in line perfectly to make a very strong, perfect, positive correlation at +1, or anything in between? And the correlation coefficient is sensitive to outliers and can be misleading when outliers are present. So yeah, if you had, something like this, I'll use a color, right? So you had this particular one right here, and yeah, that's looking pretty good. And then you have an outlier way out there. That's really going to mess up our data. So outliers are going to be misleading and mess up our data when we're talking about the R value, right? Like what if we looked at this one? So every single point is in a perfect line, but this one's like way out here, right? That's gonna be kind of deceiving, because R value it's not going to be 1 then, and really it's pretty much a perfect correlation, other than this funny piece of data out here. Okay, so it says the correlation coefficient can be interpreted as follows, and this is just kind of going over the same thing that I just said with my graphics. So I think I'll just let you look at that. And I also have this graphic that I wanted to put in. The only thing I don't like about it is, to me it's a little bit backwards, because this is the +1, and on a number line, the +1's on the right, but that it doesn't really matter that much. So it's a perfect positive correlation. Once again, is going to be all the dots form a perfect straight line. A strong positive correlation, a weak positive correlation, no correlation. A weak negative correlation, a strong negative correlation, a perfect negative correlation. And so you can, estimate what these values would be, but they'd be somewhere in between, right? So maybe this is like point, this is the positive side. So this is positive point, I'm just estimating, like maybe 3. And maybe this one's positive 0.7. And I guess we should put a 0 in front just to stay consistent with our, doesn't make a difference in the value. And then over here, just to be kind of consistent, so that's positive. So then this one over here is negative. So, something bigger than 0, closer to 0, would be something like, like a negative 0.3. And something a little closer to 1, making it a stronger correlation, making it nicer, closer to a straight line, would be something like negative 0.7, right? And then we get all the way to negative 0.1, and it's perfect. So hopefully that visual helps out. Okay, now we test you. So we want to look at these questions, and I got to flip back and forth because I just don't have a lot of space. I guess I'll continue with the red pen. Which data set indicates the strongest negative linear relationship between the two variables? Okay, well, the only ones that are negative, right, that's positive. And that's a perfect +1. And this is the only one that's negative, right? It's not perfect, but it's negative. So we're going to use the variables x and y, because that's the negative correlation. It's the only one that's negative. Which data set indicates the strongest, not a perfect, strongest negative linear relationship between its two? Which one is that? That's going to be, I said, right, A, which happens to be xy. Okay, next one, it says, for which data set is the sample correlation coefficient R equal to 1? Well, there's only one that has a perfect positive correlation, and that's going to be variables m and n. Variables m and n, so that's going to be D. Okay, next one says, which data set Which data set has an apparent negative but not perfect linear relationship between its two variables? Once again, there's only one that's negative, and it's definitely not perfect. So once again, x and y gets another one. So this is x and y. So far we have A, and we have D, and we have A. How about the last one? For which data set is the sample correlation coefficient, R, closest to 0? So is there one that's like really close to 0? Maybe it says close. I'll say approximately equal to 0. And the one that looks like it does not have a correlation would be that guy, right? I don't see a positive or negative, so we'll say that's real close to 0. And so, whoops, which one was that? That was data set WT. And that was C. All right, moving right along. Correlation. What we're trying to do on this particular piece is to understand that correlation is not the same as causation. A lot of students really, not just students, a lot of people kind of mix that up. They figure if there's a correlation, then one is causing the other. But that is definitely not true. There can be a correlation between things, but it very well may not be causing it. Here's like one study. A group of elementary school children took a vocabulary test. Turned out that children with larger shoes... So wait, these are a group of elementary school children. Okay, so we're just getting some clues here. It didn't say a grade. It said a group of elementary school children took a vocabulary test. It turned out that the children with larger shoe sizes tended to get higher scores on the test, and those with smaller shoe sizes tended to get lower scores. As a result, so there's a correlation, right? There's definitely a correlation. You go to any elementary school, and the kids with the bigger feet have overall, right? The kids with the little feet, their vocab is not as good, and then the kids with the bigger feet, the vocabulary is much better. So there's a correlation between shoe size and vocab. Now people want to then take that a step further and say, okay, the bigger your feet, the better your vocab. It's like, wait a minute, that doesn't sound right. As a result, there was a large positive correlation between vocabulary and shoe size. Does this mean that learning new words causes one's feet to grow? Or the other direction, that growing feet cause one's vocabulary to increase? And we all know that that's not true. I mean, we might be able to explain this some other way. I think we could probably be somewhat reasonable in saying, well, the people with the smallest feet would be like the kindergartners. In their vocabulary, they just haven't been alive that long. And the kids with the biggest feet, the big duck feet kids, would have to be 6th graders at the elementary school. And so they've just had a lot more years to learn more vocabulary. So it's not the shoe size, it's just time in school or experience, right? So even though there's a correlation, it doesn't mean it was causation. The big feet caused better vocabulary. Another one that I heard that I thought was good was that there's a study that shows that as ice cream sales go up, there's a correlation, a real correlation. As ice cream sales go up, so does numbers of death by drowning. And that, I know that we just took a turn for the worse on that example. But anyways, mortality by drowning goes up. So someone can say, well, there's definitely a correlation between ice cream sales go up, and then death by drowning or mortality by drowning goes up. And so there's a correlation. Someone might say, well, how about causation? Does eating ice cream cause people to die by drowning, by water? And we probably can be reasonable with that one also, saying, no. In order to do the causation part, correlation is not too hard to show. You can show it in a graph or whatever. You can show it by doing, looking at the R value. You can show it by doing line of best fit or linear regression. But causation takes a whole bunch more work to show and prove. But I think we can say, wait a minute, what triggers sales of ice cream? Well, not winter, summer probably, right? So in summertime when it gets really hot, people start buying more ice cream. But that hot also causes more people to swim. And if there's more people swimming, then there's more accidents that could happen, and so death by drowning goes up. So it's not the ice cream that caused it. So we got to be real careful about or knowing the difference between correlation and causation. So finishing up with this slide, it says the fact that shoe size and vocabulary are correlated does not necessarily mean that they are one causes the other. Okay. So, and this is the important little line here, because there are some questions that ask about causation. It says correlation is not the same as causation. In general, when two variables are correlated, we cannot conclude that the change of the value of one variable will cause the change of the value of the other variable. So in general, we really can't say causation. We could say it may or may not have causation, but we'd have to do more studies to really make that strong of a claim. All right, next problem. And these are problems that come from the adaptive side of ALEKS, right, where the little gold pie is, and you have to get there by going to the menu and hitting learn. And here's another question in that category. It says a phone company determined that an increase in income does not indicate a change in a customer's phone usage. What does the analysis show? Well, it shows that there's no correlation between income and phone usage. Next one, a music store conducted a survey. It showed that the number of CDs purchased by a shopper decreased with the number of songs that he or she downloaded. What can we say? What can we likely say? Okay. There's no correlation? No, it sounds like there's a correlation. The more CDs you buy, where did it go? Gotta go back to it. It showed that the number of CDs purchased, the number of CDs purchased by a shopper decreased with the number of songs downloaded. Okay, so it sounds like there's a correlation there. The next piece right here is at this one. Well, it says there is a correlation between the number of CDs purchased and the number of songs downloaded. However, there is no causation. This is because there is a decrease in... See, you really can't say that. There is no causation. There might be causation. We don't know. You have to do a whole bunch more studying of this thing to make that statement. So far we cannot say this and we cannot say that, because now it's making claims about causation. Either there is causation or there's not causation. We don't know. So the only safe one really to pick is this one. It says there is a correlation between the number of CDs purchased and the number of songs downloaded. There may or may let's highlight. There may or may not be causation. Further studies would have to be done to determine this, and that's what we're going to select pretty much all the time with these types of questions in this class, because unless they give us a whole study that follows it up that proves causation, we can't say one way or the other. And let's see, last one here. Yolanda compared the statistics from her team's baseball season. She determined that having fewer hits did not imply that a player caught more or fewer balls. What should she conclude? That there's no correlation between the number of hits and the number of balls caught. Yeah, that's what she should conclude. And now we are going to move on to the next set of questions. This is from 4.2. And let's see. So hopefully we got that. One of the big ideas is causation and correlation are not the same thing, and that we have these things called an R value that tells us how strong the correlation is, the association or correlation is on our linear dot plots that become linear equations or linear representations. Now, bivariate data for the quantitative variables x and y are given in the table below. These data are plotted in a scatter plot shown next to the table. Okay, in the scatter plot, sketch an approximate of the least squares regression line for the data. So you're just going to do an approximate. This, to get the exact least squares regression line, remember, and on the assignment side, HW or homework 4.2 had two problems where you actually came up with the least squared regression line, right? We came up with y hat, which is that least squares regression line, and it took some work. Of course, the book gave us a bunch of the information, but we had to know how to plug it, basically turn it into a slope-intercept form. they're not asking us to do that. They're asking us to sketch an approximate. So we're just trying to do an approximate. So let's go ahead and go to a certain color. How about red? And I want to make sure it's kind of big enough. There we go. And so I'm going to make an approximation just by eyeballing it. And so when you do this, you want your line to kind of approximate all data points. So that's pretty good, right? So the good thing about approximation, so now if this was a perfect least squares regression line, we would call it, when I say perfect, if we found that mathematically, we call it y hat. And what does this do for us? Well, first of all, we can see that it is positive, right? The slope is positive. So its R value is going to be positive. But we would go ahead and say it has, oops, I lost my, it's a positive slope, right? Its R value, I'd have to really estimate here, so I can't exactly say. Its R value is not 1, but it is positive. So maybe like 0.06, 0.0, you know, whatever. Another thing that's nice about these, about having this least squares regression line, is it gives us a prediction. It doesn't give us the exact answer, but it gives us a prediction. So for instance, if I wanted to predict what happens when x is 7, let's say, or you know, something close to 7, like right there. Darn, I kind of want that to be, let's say 7. Now you can see, if I say it's 7 and I go to my prediction line, right, so if I put in a 7, I get out about a little less, 6.75, right, something like that. Whereas, you know, you can see the actual value here, and let me partially get rid of some of this so you can see it. You know, I guess I should have put in something a little bit smaller. So if they ever ask what's the actual data point, when we put in 7 point whatever that is, 8, well, it's going to be there, right? Because there's the data point. But our predictions, whenever we predict or guess or make an estimate, it's always going to be up at the red line, okay? And so that's what that y hat is so great for, is for predictions and looking at the correlation of positive, negative. The scatter plot shows the number of hours worked and money spent on entertainment by each of 21 students. Also shown is the line of best fit for the data. Okay, so this is the line of best fit, so we might as well call it that. That guy is called y hat. They didn't give us the equation, but they do show it there. So they want us to use that. Okay, let's see. What does it say? Letter A. For these 21 points, as the number of hours x, that's this thing, number of hours, increases, the amount of money spent, y, tends to, right, the amount of money spent. So the more the person makes them, so the number of hours worked, the amount of money spent on entertainment, it looks like it's a positive, so it increases. So our answer is right there, increases. Okay, and then let's take a look at the next question here. Let's see, let me go back a sec. So the next question here says, for these 21 students, there is a blank correlation between the number of hours worked and the amount of money spent. Well, once again, this is, as I look from left to right, it's going up, so this is a positive correlation. Using the line of best fit, we conclude, or we would predict that a student working 8 hours would approximately spend what? Now, they're asking us to use our line using the line of best fit, so we don't want to go to these little points because that's the exact data. We want to go to line of best fit. So let's do that, and I'm going to use this gold color to try to do this. It's given us 8 hours, so we have to input right here 8 hours. So go like this. We need to go to our line. How come it's not snapping to this time? It's not working. We try again. There it goes. Okay, so I draw a line 8 hours up to my line, and then I go horizontally, if I can, about there. And so when I do that, I can get a really good prediction. When I put in 8, my prediction line tells me to go to left, and I get, now that's, I didn't draw it perfectly, and it's kind of hard to see it perfectly, but they give us a range of numbers or some numbers. What's that closest to? I would say that looks like that's closest. When I put in an 8, I get very close to 21. There we go. And there's the answer. Okay, use the line of prediction, right, a line of best fit, to predict. And that's what we did. Last question. The scatter plot shows the time spent watching TV. Probably should say watching Netflix on your little screen, because that happens way more than TV now. The scatter plot shows the time spent watching TV, X, and the time spent doing homework, Y, by each of 24 students last week. Write an approximate equation of the line of best fit for the data. It doesn't have to be the exact line of best fit. So we're not looking mathematically for Y hat or the perfect line of best fit or the least squares regression line. We're just eyeballing it and then coming up with the approximate equation using some algebra skills. So what I'm going to do, and I'd recommend to you, because everybody's going to get a slightly different answer, which is fine on this one. It's just going to be approximately close, and ALEKS knows that it's not going to be exact, because if you're going to approximate this line, there's going to be a range. Now, I would recommend, if you're going to approximate, I would recommend using data points that are nice integer values, because doing math with a bunch of fractions is really no fun. So instead of picking like that number right there, which would be like, I don't know, like 28.5 and up, whatever, I don't want to deal with those kind of numbers. So I'm going to do a line of best fit and try to go through these intersections, which gives me nice whole numbers. So I'm going to go through this guy right here, right? And if I go through that, see that value, let me just mark that value right there. It's 4, 24, yeah. Got to change this font size when I actually start doing the work. And then this one, I think I'm going to go through this point right here, which is 28, 4. And so that line of best fit would be something like this. Okay, so there's our line of best fit. Now we want to come up with, and I need to change that size, and I need to go to black. We need to come up with the equation of that line, okay? Now, if you remember from algebra, we're going to need to know the slope. And the slope is just the difference of the y's over the difference of the x's. Okay, so the difference of the y's, so you take the y value. I'm going to go from this one to this one, so I'm going to say 24 minus 4 over the difference, and you got to go in the same direction. Difference of the x is 4 minus 28. Okay, now we know that 24 minus 4 gives us 20, and 4 minus 28 gives us a negative 24. And in statistics, you know, in algebra, we'd probably reduce that down to a fraction so we could use slope, counting, you know, go up and left and all that. But in statistics, often, you know, we're just going to go ahead and write that as an approximate decimal. So when I divide 20 divided by negative 24, I get approximately negative, and let's round to 4 decimal places, 0.8333. So that is my slope. And now what I'm going to do is, there's a couple ways to do it. You could use slope-intercept form. Usually in algebra we use point slope form, which is just y minus y sub 1 equals the slope times the quantity x minus x sub 1. So let's put in the values that we have. Y minus, and what is y sub 1? Well, it's just a point on the line. So you could either pick this one or you could pick this one. It doesn't matter. You'll get the same answer in the end. I'm just going to go ahead and call this one y sub 1. It has to be the y value, though. So that's going to be y minus 24, because I just used this as y sub 1. And then I'm going to say equals the slope, which I found the slope, negative 0.8333, times x minus, and then x sub 1 has to be the partner of y sub 1. So you have to take 4. You can't go and grab a different x, right? So that's going to be 4. Now, all I need to do is use the distributive property and distribute, oops, that didn't work, distribute that negative 0.8333, and then, so let's do that, and we get negative 0.8333x, and here's where we can screw up. It's a negative times a negative, so that's going to have to be positive. So negative 0.83333, I said one too many, times a negative 4 gives us approximately 3.3332. Now over here on the left-hand side, we have y minus 24. We're almost there. All we need to do is add 24 on both sides to solve for y. Add 24 on both sides, and we end up getting y equals negative 0.8333x plus 24 plus 3 is 27.3332. Is that right? That's a lot of threes. Okay, so there it is. There's my approximate equation of the line of best fit. It's not, see, if that was mathematically calculated, we call it y hat. So thinking about it as y hat is not a bad thing, but we just eyeballed it, so you know. Okay, so we have that answer right, and that answer, I don't want to write it again, goes right there. Now the next question says, using your equation from part A, so this is why, you know, our answers will be slightly different, because your equation will probably be slightly different than my equation, because you may have your line of best fit like slightly up or slightly down or whatever. I think mine's probably the best, but anyways, you might have yours a little different, and it's set estimate, so we can't complain unless you made your line go like that or something really crazy. But whoops, let's see, let me do that, get rid of that. So our next part says, using the equation from part A, which is clearly this guy, predict the time spent doing homework. Predict this time spent doing homework for a student who spends 15 hours, that's going to be right there, 15 hours watching TV. Now we could just grab this and do the prediction line thing, but we want to use our little formula and show off, right? Use our formula. So all we have to do is grab our formula, y equals, let me try again on that y. Y equals negative 0, I'm just copying my formula down, negative 0.8333. Then I need to put my x value in there, and we said the x value is 15 hours. So the x value goes right there. So then it's going to be times 15. And the rest of my equation says plus 27.3332. So now all we have to do is multiply that. We multiply that, we get a negative 12.4995 plus 27.3332. And when we sum those up, we get y equals about, I mean, this is approximation, right? 14.8337. So that means by our model up here, people who spend, come on, pen, spend 15 hours watching TV, we can predict that they will spend about 14.8337 hours doing homework. And it seems kind of reasonable, right? That you know, the more you watch TV, the less homework you're going to do. Makes sense. There's only so much time in the day. And that concludes all the homework that we have done, actually. So I've done all the homework problems in the assignment side, and I've done all the homework problems on the adaptive side as well. So I hope that helped out, and you can go in and start the practice test, and then apply, and then take care of the regular test. I'll probably use this particular slide in the future, so I won't say dates. Okay, I hope this helped, and you take care. Bye.